So, does everybody understand the concept of binary tree? Okay, so we have something that we want to insert into the tree. So, what are the rules with binary trees? Do we recall? I know we just got back from break. Our brains are like, dude, I don't want to think. Thanksgiving is coming up. Why are you making us think? So, what is the rule with the binary tree?
You start at the top of the root.
The top is called the root. What are the things with no children? Leaves, right? So we got root, we got leaves. What do we just call anything that's in the tree?
Node.
A node. And what does a node have?
Left and right.
Okay, children, which are a left and a right. Okay. What else does it have? Branches. Not real trees. They got sap in them too. No, not real trees.
It's Wednesday. It's our best day.
What is the property of trees that makes them special?
Lower on the left, higher on the right.
Okay, lower on the left or higher on the right, right? So there's an ordering to them. There's one other thing that exists in a tree. So it's got a left, it's got a right, and it's got a fist. It's got a fist. No. Fail.
The mighty tree.
Hey, Spencer.
My dad wasn't around much. Could you tell?
Your dad wasn't around much. Oh, goodness. Oh, Spencer.
He went there.
Spencer, it's just clear that... Have you seen that, what is it, Volkswagen or something commercial? Okay, we're totally going to watch this. If I have a tab problem. YouTube. Dad throw ball car. Okay, Volkswagen. That was close.
Find it? All right, another one just like that. Right in the old bucket. Good toss. See, that's much better. That was good. You had your shoulder pointed, you kept your eyes on your target. Let's do it again. Watch me. Just like that one.
The durability of the Volkswagen Passat. Pass down something he will be grateful for.
Good arm.
That's the power.
Anyway. Sorry, Spencer. That was at your expense, but
No, it's fine.
I totally do things wrong too. Okay, what else is it? What else does the tree have other than the ability to not throw?
Where'd the ball? Oh, you got it. It's good.
What else do we have? What is the crucial part? It has something in it. A trunk.
We have a hint.
Well, it's a data structure, so it has
Data.
data. Right? So we have to have some value associated with it, right? So the value could be something simple, right? Typically, remember when we talked about the example, we had social security numbers, right? So everybody has a social security number, or, right, university now we have NUID, right? Nebraska University Identifier. Right, so we have to have some sort of value associated with it, right? So if we were defining this in C, how would we create a node that exists within a binary search tree? Type def. Are you saying that I'm deaf to type? We'll go on this side. Okay, so you say type def struct. Somebody will go turn off the other light. Oliver, you got it? Node. Okay.
Oh, that's glorious.
You can read my bright green colors. Okay, so what has to be inside of the node? What did we say there had to be?
Some data.
Some data.
Let's go. It's going to be an int.
An int. Data.
Of course.
Of course. What else do we have? Well, so we normally don't keep track of the parents, right? So we're always, when we traverse a tree, right, we always are actually traversing down the tree. So we always start at the root and we go from the top down. Now, there are trees. So for example, Java keeps track of what the parent is so that it can actually do some traversal efficiently. So what, if we don't have parent, we would have what? A left node and a right node. So what, struct, what should I type here? Node, what?
Pointer.
Pointer. We have what, left? Lefty, yep, lefty.
And a righty.
And righty. Okay? So we have to have the data, right? We could include it in here. So why do we have to make these pointers? Nobody understands pointers, and so they don't make any sense. Why do I have to use pointers?
Because you need the address to where the data is.
Because you need the address to where the,
Structure.
yeah, the other node, right? So when we're drawing the picture, right, we're just drawing like, I have the number 10, and then I have, what are some examples for this one? 5, oh, great number. How about this one? What? 15. Wow, you guys are imaginative with your numbers. Me too, but, right? Right, so we have to have the property that each one of these has a left and a right, right? And these actually have left and rights, but, right, they don't point to anything. So what should we set them to? Null, right? Correct? Right, there's also a, so sometimes they'll actually use what's called a sentinel value, so they'll make it point to a node that is the, like, leaf node, right? And then make all of them point to that, and then they do a comparison on it. But really, so that part is not really important. So, when we're inserting stuff into the tree, right, if we insert into a blank tree, where should we put the date? Where should we put the data, right? It should become the root of our tree, right? So if we have a root and we insert, how do we decide where it goes? I think here I need a node and a semicolon, or stuff just goes crazy. So let's say we want to add a node.
Forgot your H on. Because, yeah, you missed the dot on there.
You guys ever watch Willy Wonka? Right?
Yeah.
H dot. No, reverse that. Okay. So
Which part of that?
it's in the old one, right?
Oh, I know.
He would mix up the words, and then he would say,
Wait. Reverse
reverse it, right? Okay, see again, my age. Oh, coming out. All right, so let's say we want to add a node. Okay, so what we're going to do here is we're always going to return a pointer to, well, we'll do the special case inside of the other one. So here we'll just return nothing. So what do you think our signature would be for our add function? We want to add a node, or I guess the technically correct term is insert, right? Because you're inserting it into the tree. So let's say you had, what are the parameters that we need in order to insert a node into a tree that we just got talking? We want to insert 44 into the tree we just made. So we'll assume we built the previous tree and we'll work on that.
We need to know the node.
Okay, and what type is the head node?
Node pointer.
And we'll call it the root. What else do we need?
The data.
Well, we won't call it data, right? We'll say node pointer new node, right? So it's a new node that we're adding to the tree.
Don't you also need to know the value?
So I'm going to assume that I've already filled that in,
Okay.
right? So I'll start off with, just so we have, for the sake of doing it in class, right? What do I need to put in here? Size of what? Node. And how do I set the data? Arrow data equals root is 10, right? Excuse me. And then what should we set left and right to? Well, I'll go ahead and just set the right. Oh, well, let's do both of them. Oop, it's not left, right? That's lefty and righty. Okay. So we're gonna make a new node. Okay. So we want to insert onto root Bob. Does that make sense? All right, we're going to add Bob to the root node. And we're going to make another method to just create us a node because I don't want to retype those 4 lines every freaking time. So we're going to change that. Okay, so we're going to try and insert into here. So what do we need to do in order to decide if it goes on the left or on the right? Okay, so we're going to compare. We're going to say if, what? Root arrow data. So let's say it's less than new node arrow data. So what do you think we need to do?
Root dot righty, or not dot, root righty is equal to new node.
So he wants to say root arrow righty is equal to new node. In general, is that right? It's okay, Spencer, you can be wrong. Why would that not be right? Okay, let's think about the general case, not just the specific case. General case is, I have a tree.
If it's equal to null.
If it's, okay, so we got to check for null, right? So if it's null, then you're right, Spencer. Right, so if root arrow, what do we say, righty? Is null, then we're just like, dude, this doesn't have a right. I got something that's bigger than it, so I might as well set the right. And we need an else here, right? Else, so what do we do if its right is not null. So let's say we're inserting 44 and we have this tree. What do we need to do? What? Move the root node down. Well, yeah, remember we're changing a copy of it, right? What do we need to call? It's almost like if we had a method that could do this. We call insert, right? And what is the root that we're going to give it? No. Where are we inserting it? We're inserting it into righty. Root arrow righty. And new node. Does that make sense, right? So we're calling the function and we're saying, yeah, we're not at the actual root, but we're pretending we're at the root of this new subtree, which is, right, going to be hopefully smaller than the entire tree, right? It's at least smaller by one node. We know that much, right? Because we just took out the old root. Okay. Else, if what? So we checked root arrow data is less than, greater than. Now here we're just, I mean, it's going to be very much similar code. If root arrow lefty lefty yeah, it's such a pain. It's such a pain compared to other editors, but that's okay. So we're going to call insert on root arrow righty new node. There we go. Mate, I don't know what you're talking about. I don't see any missing semicolons. Okay, so this is our generic insert method, right? So we're inserting into a root, inserting a new node, and we just need to traverse the tree until we find the spot where left or right is equal to null based on what we're trying to insert. So I'll make one more method. So we will write a method to do a print because we will want to print out the data that is in our tree. What do we need for our print method? Pointer, root. Now, do we remember? So what are the 3 different types of traversals that we can do on a tree, which were covered in the book?
I forgot to read the book. My book doesn't work.
Your book doesn't work. My book works. I don't know what you're talking about.
Did he click onto the module? Click it.
The modules just don't like us. But let's see.
Post order.
Post order. All right.
Maybe pre-order.
Maybe pre-order. One more kind. Post, pre,
Order.
order. No. In order, right?
Oh.
In order traversal. Does anybody, now that we've jogged our memories of the chapter that we have read, what is the difference between pre-order, in order, and post order? If we have a tree,
Which children you go to first?
which children you go to first, right? So with pre-order, you visit a node first, and then you visit its children. With in order, you visit a node, then you visit its left, which are the smaller things, then you visit the right. With post order, you go and visit your children first, and then you visit you last, right? Correct? Sure. Right, so if we want to see if our binary tree is working, which order would give us the values that are sorted, right, in appropriate order, actual order? In order. So we will visit our left, right? Correct. And then visit ourselves, and then visit our right. Right? Because if we look at this one, right? Visit our left, 5. Visit ourself, 10. Visit our right, 15. Right? That gives us the actual in order sorted type of method, right? And we spend a lot of time talking about sorting in these types, like this type of class, right? So sorting is a big thing. There are lots of different algorithms that we can use. If we have time, hopefully we will get to some of the sorting algorithms. So what we're saying is we need to visit our left, or how would we decide if we need to go down the left-hand side? If root arrow lefty not equal to null, what are we going to call? If lefty is not null, what do we call? Print okay. And then we need to visit ourselves. I'll put quotes around it so it looks nice. Root arrow data. And then if root arrow righty is not equal to null, right? Because we're doing basically the same thing. Print I was just going to say, are there any corrections, code Nazis? And they found one. So that is true. I like it that you find them earlier. But you know what? Eclipse sort of does this. It's like a problem that's already solved. Okay, so we're going to go ahead and call print on root. Hopefully, prints off.
Won't it only print the roots?
Won't it only print the roots? Well, let's see. Right, because remember, it's checking the true reversal. We've taken root and we have inserted Bob right into that. So I already took Bob and I put him into root. So now when we go through our print function, right, Bob is going to be on which side?
Right.
The right. So root arrow righty is not going to be null, right? It's going to be pointing to Bob, right, which is what our node was.
Right, so then how does it print something?
It calls print, right? Print, if you come back up to the top, print will check left on Bob. Left on Bob is null. It'll print itself, which is the value for Bob, and it'll check right, which is also null. Right, so we can, I keep saying right. So we can keep inserting nodes. Let's make one more method, which is the one I wanted to make earlier. Node pointer get node. I don't want to manually type in all this. So there's what, 4 lines there. Yank for yank. Put I'm lazy, I'm not going to rename it. If I was in Eclipse, I would, but I'm not in Eclipse, so. Okay, so now I can insert nodes at my leisure, right? There we go. Get node. I gotta do my prototype, correct? You think we did it right? Oh, no compile errors. Look at that. 0, 10, 44, 100, right? If we were ingenuitive, right, we could write it so that this would ask the user for what number they'd like to add, and then it would add it to the tree.
Do you have a case of the values are equal?
So we don't have a case of the values that are equal. So it really depends on what type of data you're storing. So right now, basically, we're ignoring the fact that you just added a new node that has an equal value.
Okay.
There are some trees that allow you to have basically a list of items that are at a particular location. So your key, when you get out the set of keys, you would get out a list of data items as opposed to just a single one. So that really depends on implementation, right? If I was in Java, I might throw an error saying duplicate key, or you just silently replace it, which is kind of what Java does in their implementation. So one of the things that we have with this, right? So if we insert the data in here, what is a bad case for how we insert data? Can anybody think of something that would be a bad way to insert data into a tree like this? What if we inserted,
You,
go ahead.
I'm thinking if you have like a big number, and then like you, I don't know where I'm going with this, but like,
If you have a big number,
right, and you insert it, and then you go back to a smaller number, then like they won't be. Maybe I have it backwards now.
well, here, I'll do an example, right? So let's say I insert the number 1, right? Then I insert the number 2. Where does 2 go? To the right. And then I insert 3. To the right. And then I insert 4. To the right. Right? So I keep going to the right. What does this look like if I wouldn't draw it at an angle? A linked list. Right? So what was the benefit of having something in a binary tree?
Not having to traverse the whole list.
Not having to traverse the whole list, right? The benefit is if I have numbers between 1 and 64, I guess the number 32, and I just cut my search space in half, right? And the number of times I do that, anybody remember what we figured out? What was the mathematical backing of that? How do we figure out how many levels we have to go? It was a log of something, log base 2. Right, so log base 2, the easy way to think about it is if I take the number 2 and I raise it to a power, let's say 10. That is equal to 1024. So the log base 2 of 1024 is 10. Or how many times do I have to multiply 2 in order to get that? Right? 2 to the 8. What's 2 to the 8? 2 to the 8 is what? 256? So log base 2 of 256 is 8, right? So the benefit is if I took a really big number, right, I said, what, a billion or something, and I do log base 2 of that, remember we did this in class, and I have to do like the log of 1 with lots of zeros. Right, how many zeros did I put in there? There's 3. 10 million, right? So if I had 10 million users, and if I had a perfectly balanced tree, right? So every time I cut my decision in half, right, it would take me 24 searches through my tree, right? 24. Is it bigger than this or is it smaller than this? In order for me to get to the final result. Right? 24, right, is our worst case if it's balanced. Or 25, right? There's plus or minus 1 in there. Wouldn't getting it to be balanced be a pain? It would be if there was no algorithm to do it, but there is, and we will talk about that. So we're going to talk about red-black trees, which are what we call self-balancing trees. So there's a really cool visualization which I'll bring into class and we'll look at that shows how it actually does the balancing, and we'll go ahead and just insert stuff in order and see how it goes ahead and rejiggers things. Okay? Yeah, rejiggers. That's a technical term.